In the last class, I explained speed of a flux and Venturi meter. And in today's class, I will explain some more applications of Bernoulli's principle. Applications of Bernoulli's principle. So first I will write the Bernoulli's equation that you know, that is pressure energy per unit volume plus kinetic energy per unit volume, that is half rho v square, plus potential energy per unit volume at any points in a flowing fluid is constant. Okay. Then in today's concept, I will explain aerofoil or aerodynamic lift. Okay. So aerofoil or aerodynamic lift, that means you may have seen the wings of the aeroplane. That is, the wings of the aeroplane is designed in such a way that it should get some upward lift. Okay, that means if aeroplane is moving in one direction, means definitely opposite to that aeroplane, the wind will also move with some velocity. There will be a relative motion between aeroplane and wind. So in this case, we will represent that flow of wind or flow of fluid in streamlines, and this is the shape of the wings of the aeroplane. By having this type of shape, what is the benefit means? So here you can see there is some convex shape in the upper side, and this shape is slightly, we can say, concave shape. Then the plane is moving in this direction. This is the wing of the plane that is moving in this direction. The air is moving in opposite direction. So I am representing that flow of fluid in streamlines. Below the wings, I can able to draw with a straight line. But here the fluid particles or the fluid elements cannot penetrate with this wing, right? So how they will move means, how can I represent the flow of fluid element means with this shape. Okay. Above the wings, these are the lines of flow. In this way the fluid elements will move. Okay. Below the wings, I can able to represent with straight line. So you have to consider relative motion. The wind is blowing in opposite direction, the plane is moving in this direction. In that case, what happens means, let us consider any 2 points. I am considering here. This point is A, and this point is A, and this point is B. I will mention that point B here. Okay. So definitely the wind is blowing in this direction, means in T time these two fluid elements crosses this wings of the plane. Then in T time the same two fluid elements I can represent somewhere here. Okay, this is A point and this is B point. That means here at the same time, in the time interval T, both the fluid element crosses the wings of the plane. So you can see in the diagram the fluid element at this point has to travel the curved path, and the fluid element at this point I am represented with B has to travel the straight path, but both will crosses or both will reaches this point at the same time t. Then which fluid element will move faster, or which fluid element has to move faster? So you can consider an example also. Here there is a person. At the A point you can consider a person. This person also running with some velocity, and at B point another person, B person also running with some velocity. They are starting some same point and ending point is also same. Both will reach the ending point at the same time. But what is the difference here means, this A person has to travel the curved path and B person has to travel the straight path. Definitely this distance become more, right? So at the same time the A person has to reach this end means definitely the A person has to travel with more velocity. So the concept here means, above the wing the streamlines are representing, so that will move very faster, and below the wing the fluid elements are there, this will move with less velocity comparing to above streamlines. That means I can able to say that above this wing the velocity is v1 if I represent, below this wing I can able to represent the velocity of the fluid as v2. Definitely we can say that v1 velocity is greater than v2 velocity. So what happens here means, here velocity is more, here velocity is less. In this expression the wing is at same height means this will remains constant. So this will remains constant. At this point the pressure energy P1 of rho V1 square if I write, below I have to write pressure energy per unit volume P2 of rho V2 square. Then if velocity increases, it should be constant. The total energy at 2 points, at this point and this point, it should be constant. If velocity increases, definitely what happens means the pressure will decreases. Remember, so it is same means that is always remains constant. Here variable things is pressure energy per unit volume and kinetic energy. So here velocity more, hence pressure become less. So at the bottom velocity is less, hence pressure become more. So V1 is greater than V2, hence I can write P1 is less than P2. That means here below the wing P2 pressure is more, above the wing P1 pressure is less. Due to difference in pressure, definitely a net force will act in upward direction. Okay. So because of this net force there will be some upward lift. Okay, like this we can understand the concept of aerodynamic lift or aerofoil. So this is one application of Bernoulli's principle. And next one, one more application of Bernoulli's principle, that is roof of an hut blown off. So in day-to-day life you may observe this thing. So let us consider a hut. Okay, so this is the roof. So usually the roof of an hut means they will place a wide sheet, isn't it? Then during storm what you may observe means the air outside the house or above the roof will move very fast. So inside the house definitely the air will blow. That means the speed of the wind inside the house is little bit less comparing to outside the house. So in this case what happens means, again I said in last concept, so if you consider this is constant, just you concentrate on P plus of rho v square. Why? Because it is the same. If velocity increases, to maintain the total energy constant, definitely the pressure will decreases. So here where the velocity is more means above the roof. Velocity V1 I am representing, and inside the house or hut the velocity is V2, and I can able to write V1 velocity is greater than V2. So above the roof there is some pressure. Because of high velocity the pressure is less comparing to pressure inside the hut. Again what happens means there will be a difference in pressure. Difference in pressure is created. So due to the difference in pressure, here pressure is more, here pressure is less. Hence again we will get some upward lift. Because of that upward lift, the roof of an house will blown off. This is one application of Bernoulli's principle. Okay. One is aerofoil. For the aeroplane also it needed upward lift. Because of that the shape of the aeroplane, last example I have drawn, like that they will maintain. By maintaining in that shape, it will give some upward lift. And so one more application in Bernoulli's principle, that is spinning of ball. Okay, let us consider a ball, okay, a tennis ball or a rubber ball. So first case let us consider this is without spinning, it is moving in this direction. Definitely the ball is moving in this direction. Relative to the motion of the ball, the wind will move in opposite direction. Then how can we represent the lines of flow for the air means, we can able to represent the lines of flow in this way. This is the motion of this is the path followed by the fluid elements. Okay. So in the below also you can see the same path. The fluid will move opposite direction to the motion of the ball. This is the flow of fluid elements. And I explained in aerofoil example, like that you consider a 2 points, one point A that is above the ball and another point B that is below the ball. So at the t time these two fluid element crosses this ball and it will come somewhere here. Let us imagine these two fluid elements in the time interval t, these are moving, isn't it? In time interval t, definitely these 2 points will crosses this ball and they are at this point. Okay. Then what is the path followed by this A fluid element? The same path is followed by B fluid elements. Why? Because of that the distance is same, time interval is also same, both are reaching this point. Then we can able to say both are moving with same velocity, sir, both are moving with same speed. So because of same speed, V1, if you consider the fluid element speed above the ball, V2 is the speed of the fluid elements below the ball, both are maintaining same speed. Hence I can able to say that V1 speed is equals to V2 speed. There is no difference in velocity. There is no difference in velocity means there is no difference in pressure. What is the pressure present above the ball? The same pressure will present below the ball also. So in this case there will be no upward force. When we will get some upward force means when there is a difference in pressure. And we are discussing about spinning ball, right? Spinning ball means, so the same ball you consider, first example I explained, the ball is moving without spinning. In the second case you may observe that the ball is spinning in this direction. Okay, spinning means it is rotating at the same time it is moving forward. In this direction the ball is moving, and definitely the wind will move in opposite direction. What happens means when the ball is rotating, the air molecules are attached to the ball. That ball will drag all the air molecules. I will draw the diagram, then you can able to understand. While spinning, whatever the molecules are present on the surface of the ball, this ball will drag all the molecules. Okay, so the air molecules are very crowded above the ball. Why? Because it is dragging that air molecules. If you see below the ball, you can observe the streamlines like this. Okay, so now based on two examples, definitely you can able to say that where the speed is more and where the speed is less. Definitely the speed of the fluid elements above the ball is more. So if I consider the velocity above the ball is v1 and the velocity of the fluid elements below the ball is v2, definitely here it has to travel more distance. Here the fluid elements has to travel less distance. Hence here the speed is less, and here the speed has to be more. So v1 is greater than v2. v1 is greater than v2 means definitely p1 is less than p2. The pressure above the ball become less and pressure below the ball become more. So what happens? Again it will get some net upward lift. So this upward lift it is getting due to spinning. If the ball is moving without spinning means it will not get any upward lift, isn't it? So here one definition we can able to write: the upward lift due to spinning. Okay, the upward lift due to spinning is called as Magnus effect. So these are the applications of Bernoulli's principle, and this Magnus effect definition is important for 1 marks. I hope you understood this concept. Okay, remember the upward lift always we will get whenever there is a difference in pressure. Where velocity is more, their pressure is less. Where velocity is less, their pressure is more. We can able to say according to Bernoulli's principle. And one more day-to-day life example I will tell, that is let us consider a railway station platform. Okay, sometimes what happens means any person standing at the edge of the platform. So this is a platform and the person is standing at the edge of the platform, and you can consider this is a railway track. Suppose the rail is coming with high velocity. Okay, the person standing at edge, the rail is coming with high velocity. Definitely the air molecules attached to the rail also will come with high velocity. In that case, definitely if you are standing here means the air blowing in front of me, it is blowing with very high velocity, and the air blowing behind me, what happens means that velocity is relatively less comparing to the air blowing in front of me. Again So here the pressure is decreases. Why? Because the air velocity is more in front of me, right? And behind me the velocity of air is less, means pressure is more. So what happens means again there is a difference in pressure. So definitely what happens, there will be a forward push. So always remember, one should not stand at the edge of the railway platform when the train is moving with high velocity. So by this the applications of Bernoulli's principle is completed. And the next concept is viscosity. For example, let us take a water in the beaker and you pour that water on the floor. So the water will move with some velocity. After that it may stop if force is not continuously applied. And also in another beaker you take an honey and that honey you pour on the floor, and you will observe that the speed of the water is more and the speed of the honey is less. Why? Because that honey is a thick liquid. In that case we can define which is having a more viscosity and which is having less viscosity. So for that to understand, let us consider a surface or a river belt, a bed. On this surface, so here the fluid is flowing. Okay, in this direction the fluid is flowing, and the flow is we will consider steady flow. Steady flow or streamline flow means definitely we will represent with these stream lines. And also you have to imagine the fluid is flowing means it consists of so many layers. Okay, so these are streamlines, or you can able to consider there are so many layers, and the bottom of the layer is attached to the floor. And in this case you may observe that the different layers will maintain the different speed. The layer which is attached to the floor, that layer velocity suddenly becomes 0, and the layer just above that surface, this layer it may move with some velocity, let us say 2 meters per second, and the layer above this layer it may move with some velocity 4 meters per second. Like this, the height increases from the surface, the layer's velocity also increases. And one more thing, to understand this viscosity concept, you should know about friction. Okay, so actually this viscosity is defined as, it is a property of fluid by virtue of opposes the relative motion between adjacent layers in the fluid. Okay, so here what is meant by friction means, let us say this object, if you apply force, this object will move with some velocity. So in this example, this object is not in contact with any surface. Suppose if you consider a surface and consider the same object. Now that object is moving on the surface means, now we can able to say that there is a relative motion between the surface and object. Okay, and now it will not move that speed as it had moved earlier. Definitely the speed of this object will decreases. Why the speed of the object will decreases means, when there is a relative motion between two objects, that means a force will comes into play. Which force means that force is called as frictional force. That frictional force always opposes the motion of the object. Once again I will repeat. When there is a relative motion, what happens means, a frictional force will comes into play. That frictional force opposes the motion of the object. If there is no relative motion means there is no friction. Here also different layers are there. No, you have to imagine that between the layers there is a relative motion. One layer is moving upon the other layer, like playing cards. Okay, take a set of playing cards and apply a tangential force. Now you can able to imagine that motion of the playing card. That the top card will move with more velocity, and the next card's velocity will decreases. The final card is attached to the floor, right? That card definitely its velocity become 0. In the similar type, if you consider the viscous force, definitely in the similar way the fluid will move. That means the top layer is moving with some more velocity and the bottom layer is moving with little less velocity. If we consider this is 8 meter per second, this will move with 6 meter per second, this will move with 4 meter per second, like that it will move with 2 meter per second, and the final, the layer attached to the ground will comes immediately to the rest, hence its velocity become 0. Here also there will be a relative motion between two adjacent layers, and this will come immediately to rest. Then what happens means, this is contact with the above layer, so this will apply force in opposite direction. There is a relative motion between two layers, hence which force will comes into play means frictional force will comes into play. And in which direction the frictional force will act means, the frictional force will act in the opposite direction of this motion of the fluid. So this force is also called as drag force. So here this layer opposes the motion of the above layer. Okay, so it will apply force, the force will exist and it will act in the opposite direction. But the above layer, it is moving with 4 meter per second, right? This will also apply force on this middle layer and it will pull this layer in this direction. Okay, and if you consider this layer having some relative motion with below layer. This below layer will drag the above layer in opposite direction, but this above layer will apply force on this layer and it will push in forward direction. Like this, the frictional force will comes into play in every adjacent layers, and the frictional force will always act in opposite direction to the flow of fluid. If you consider this point as A, okay, this layer, this fluid, in this layer the fluid element is moving with some velocity. That velocity you consider it as V, and this layer is at a distance. How much means? The distance is x. And next above layer you consider, okay, the above layer I will consider the distance, that is x plus dx. If it is 1 meter means it is 1 meter plus this distance is dx, very small distance dx means, that you can consider as 0.001. So 1 plus 0.001 meter you can consider. That is the meaning, x plus dx. And here this velocity is v means definitely we know that in this direction the velocity will increases. Here the distance is x plus dx means definitely you can consider the velocity is v plus dv. Here dx and dv that indicates a very different, that means infinitely small change in distance, very small change in distance. Or dv means infinitely small change in velocity, very small change in velocity. Here I am representing 2 meter per second, means v plus dv means you can consider 2 plus 0.001 meter per second, like that you can consider. Okay, and one more word we can able to say that here dv by dx. Okay, that means here by moving the distance dx, by moving the distance dx, how much velocity has changed? The velocity has changed is dv. Per unit distance, what is the velocity means? Okay, what is the change in velocity means? You can able to write it as per unit distance, the change in velocity is, you cross multiply, you will get, that will become dv by dx. This is called a rate of change of velocity per unit distance. Okay, change in velocity per unit distance, or this is also called as velocity. This is also called as velocity gradient. Okay, remember dv by dx means velocity gradient, and experimentally it is found that, you know that viscous force will act in opposite direction. To maintain the flow, we need to apply external force in the same direction, and experimental study states that this viscous force is directly proportional to area. If the layer area is more, then more frictional force or more drag force. That frictional force or drag force is nothing but viscous force, and this viscous force is directly proportional to velocity gradient. That means you can say here, this is a top layer moving with 8 meter per second, the bottom layer is moving with 6 meter per second. What is change in velocity here? Per unit distance, if you consider, that is 2 meter per second. Okay, some viscous force is acting in opposite direction. If you consider top layer is moving with 12 meter per second and bottom layer is moving with 6 meter per second, then change in velocity becomes 6 meter per second. 12 minus 6 meter per second. The change in velocity per unit distance increased. Hence, in the opposite direction, the viscous force also increases. Based on the area and velocity gradient, the viscous force depends. Okay, so finally we can write that viscous force is directly proportional to area into dv by dx. Now we want to remove the proportionality constant. To remove the proportionality constant, definitely we have to write some constant value. Here we can use that constant value as eta. Eta into a into dv by dx. Then what does the eta means? What is the meaning of eta means? It is called as coefficient. It is called as coefficient of viscosity. It is called as coefficient of viscosity. This eta depends on nature of the liquid. For water, it is having some value, and for kerosene or other fluid, it is having different values. And if eta value is more, then what happens, you see here. So we came to know that force expression is eta multiplied by area dv by dx, right? Then here the viscous force, how the viscous force will act means tangential to the surface. Okay, so in the mechanical properties of solids also you have studied. On this block, if you apply tangential force, then there will be a relative displacement between two extreme layers. The same concept here also we can apply in fluid also, but what is the difference means here it will attain equilibrium, here it will continuously flow in one direction. Everything the concept is same except equilibrium. Okay, and so here also the viscous force will act tangentially to the surface, to the plane surface. Then that force comes to be 10 units, and this eta value I am writing as 5 units, or I will write it as 2 units. Area I will consider as 1 meter square, unit I will consider. And this rate of change of velocity, it is 2, area is 1, means the rate of change of velocity or velocity gradient value should be comes to 5, right? Then only both side it will be same. If you consider the velocity gradient is 2.5, okay, or if you consider another liquid, for example this is water. For water, its coefficient of viscosity, let us take it as 2, then velocity gradient, let us take it as 5, and the viscous force we are obtaining, that is that means the viscous force here generating, that is 10. Next you take another liquid, that liquid viscosity, coefficient of viscosity is different, let us take it as 4. And the viscous force generating also let us consider it as 10. Automatically what happens? The velocity gradient will decreases. Then for the water, the velocity gradient, change in velocity per unit distance, it comes 5. For other liquid, coefficient of viscosity more, hence the change in velocity per unit distance will come less. We are getting 2.5. The overall meaning is, or what we can able to conclude means, if coefficient of viscosity is more, that liquid will move with less speed. If coefficient of viscosity is less, that fluid will move with more velocity. Okay, like that we can understand the coefficient of viscosity. It is depends upon nature of the liquid. Okay, this is the expression for viscous force, and you can able to represent with minus sign. Why minus sign? Means the fluid is moving in this direction, the velocity is in this direction, the viscous force is acting in opposite direction. Always frictional force will act in opposite direction, and it tries to oppose the motion of a body. Okay, if we are not maintaining the force in this direction, definitely after moving some distance, the motion of the liquid becomes that means it will ceases its motion. Then I hope you understood the concept of viscosity, and also you came to know on what factors the viscous force will depend. That is viscous force F is equals to eta into A into dV by dx. And what is the SI unit of coefficient of viscosity? Coefficient of viscosity we can write it as F by A divided by dV by dx. So this is nothing but stress. You have studied in mechanical properties of solids, that is tangential stress. Here also the force acting tangential to the surface means force per area. The viscous force is applying a tangential stress. This is velocity gradient, force by area, that means you can write it as Newton per meter square, divided by, here change in velocity, meter per second, divided by distance, meter will get cancel. The SI unit of coefficient of viscosity is Newton per meter square into second. Okay, remember this is the SI unit of viscosity. Okay, then you can able to write the dimensional formula of coefficient of viscosity. Dimensional formula becomes for Newton mLT to the power minus 2, and for meter square L to the power minus 2, for second T to the power 1. Okay, then overall you will get the dimensional formula of viscosity. Coefficient of viscosity becomes m L, here minus 2, here plus 1, it become minus 1, here minus 2, here plus 1, hence it will become T to the power minus 1. Remember the dimensional formula of coefficient of viscosity. And one more thing you have to remember, that is, if we take the area if you take in unity, and the rate of change of velocity gradient also if you take in unity, if we make A is equals to 1, that means the area I am considering 1 meter square, and the change in velocity per unit distance also I am considering as 1 meter per second, the area is 1 meter square, then numerically the coefficient of viscosity eta will be equal to this viscous force. And one more unit is there for coefficient of viscosity, that is also called as decapoise. Okay, so SI unit of viscosity you can consider it as Newton per meter square into second or decapoise. In CGS system its unit is poise. That means Poisson, a scientist name, he studied about this viscosity. To give honor, we have kept his name as unit. Thank you.